Live on the internet. Hello, welcome back. So we're going to play around with frequency histograms, which we've been doing pretty much all quarter. And I'm just going to give a different twist on them today. So for some reason, I've been obsessed with pulse rates. And this is ridiculous. It's like, why am I obsessed with pulse rates? And then it hit me this morning. Oh, yeah, my heart's been acting up. Right, okay. Last year, I was obsessed with body temperature for some reason. So next week, I will come in here with a bunch of thermometers, and we're all going to measure our temperature. There'll be the infrared forehead kind. And we'll see what is average temperature, what is above average. Like, how do we know somebody has a fever? Why do we think those numbers are significant? Right? So there's some math behind that. Take a look at. So pulse rates. I collected your pulse rates. I met a guy from Washington at the University of Puget Sound that has collected thousands and thousands and thousands of students' pulse rates. We sampled some of that at the last exam. This is your pulse rates right here. And I made some histograms on it, and I made a few different kinds. So the most frequent kind we've made so far are frequency histograms, where we have the computer count up how many are in each group. And there's a lot of ways we can make groups. The computer wants to know what's the highest number for each group. But my mom often doesn't get that on the picture. And so I need a human readable one. Sometimes the human readable one would say, these are the 50s and these are the 60s. Sometimes it might say 51 to 54, 55 to 59, right? So we have different ways to make them pretty. I chose this way because it was easy. Does that make it the best possible histogram I can make? No, I gotta make a bunch of different ones and then use my best judgment as to which one's the best. We never know from our first try. Relative frequency history are ones we've played with. We've also played with cumulative histograms a little bit in the homework. I haven't used them much. We're gonna start using them soon. So I just have some examples of each of those. So here is the frequency histogram. Any comments about it? It's kind of bell-shaped, yeah. And there's some belief that pulse rates should be normally distributed. Okay. Although science and a lot of statistics says that many, many, many things are normally distributed. In the sampling I've done and my peers have done, they're hard to find, even though they're supposed to be everywhere. But there's another important reason why we look for normal distributions we'll get to in a couple of weeks. Okay, pretty bell-shaped. So next I'm going to show you the relative frequency histogram. Ready? Hold on. Drum roll. There's the relative frequency histogram. Looks pretty different, huh?
Yeah. Looks different.
Doesn't it? What? Okay, let's see. Relative frequency histogram, frequency histogram.
Like this. Oh, different. Oh,
what's the difference?
Higher up, it shows that more.
Oh my God, they're the same shape. Everything's the same size, except the scale is different. Yeah. Whenever we change from a frequency histogram to a relative, we're just renaming the scale. It is the same graph. So really, you could make one graph and just draw a couple of scales next to it. Okay. All right, I'm going to show you another one, and then I'll explain it, because I'm pretty sure I haven't talked about this at all. Another popular histogram out there is called a density histogram. And you probably haven't seen that in the book yet. Here's the density histogram. Density sounds pretty intense, doesn't it? Whoa, that's dense. And it looks pretty different too, doesn't it? Wait a minute, it looks exactly the same, but with one exception. What's the exception? The scale. Okay. Sort of. They're at the same level, but the numbers are different. Okay, so here's the relative frequency. It peaks out at 5.5, 0.375. If we look at the density one, oh wait, it's 0.05.
So it puts another 10.
Okay, so how the hell did I calculate the density histogram? I'll demonstrate that in just a second. Okay. What will look very different will be the cumulative one, because the cumulative adds up all the previous stuff. Okay. So what this column means, that's not how many people were in the 60s, it's how many people are in the 60s or less. This column right here is not how many people had a pulse rate in the 70s, but how many people had a pulse rate in the 70s or less. It adds all the previous stuff together. So I could use this to answer a question like, what's the probability if I randomly pick somebody that they have a pulse rate less than or equal to 79? And I look at this and, well, that's a 75, that's close to 75, maybe it's like 72% of people have a pulse rate, 79 beats per second or less. They're already added in here.
Okay.
Yeah, that's the whole
That's
accumulation.
the cumulative.
Accumulate means to put together,
That's right.
right? And so it puts together. So how tall is the last stack, the 90s?
Because it's all of them put together.
Okay, and that represents what percentage? 100%. Yeah, so we said, okay, what percent of this group had a pulse rate of 99% or less? All of it, 100%. And that's the point of a cumulative distribution. And we will be seeing cumulative distributions more and more. Sometimes when you push a button on the calculator to get an answer, or you push a button on an Excel spreadsheet, some of the time it gives a cumulative answer. And we have to differentiate. When was it a cumulative answer, or when was it only this group? Okay, and that's going to take some getting used to. We're going to mess it up at first a lot, but then we'll get used to it. So I'm introducing it early. So let's go back. Frequency histogram. Divide by how many, and you get the relative frequency. Okay, let's figure out the density. So I'm going to try and steal that into my chart here. Snipper, where's my snipper? Right there. And snip. And copy, new page, paste. Okay, so here's that. So what does density mean? So think about where you might have used density somewhere else. Anyone give me an example of density outside of statistics? Science, like weight? Okay, so give me an example.
Well, if something is more dense than water, then it's not going to float.
Oh, if something is more dense than water. Okay, so like I'm a pretty skinny, bony guy, and when I go to try and float, I don't unless I'm holding a big breath of air. If I let that air out, I sink. Okay. My wife is a lovely, voluptuous woman, and she floats with no efforts, and it always upsets me. I have to work hard to swim. She does not. Lead versus wood. If I had two balls, one was made of lead, one was made of wood, and I dropped them both on my feet, they would hurt the same way? No, the lead is way more dense. It's got more stuff in it, right? Okay, so what is density? If you ask a physics guy would say density is stuff divided by space. And I'm making a very loose definition there for a reason. So I used to teach high school, middle school, and elementary school. And you're always, when you're a teacher in one of those schools, you're always telling kids to line up, stand still, be quiet. And if kids are densely lined up, there's trouble. They're pushing each other in their elbow room and personal space and stuff. So if I spread them out a little, I'm going to have less trouble unless they get too spread out, because then they're like cats, and I got to bring them back together. So that's an example of they can be dense or they can be not dense. We could all be crowded in a room together. In this room, we're very spacious, aren't we? If we were all thrown into a closet together, we'd have some trouble, right? Or into a Prius. If we all tried to fit in a Prius together, that would be a problem. Clowns in a circus. So amount of stuff, you put it in space. We call it very dense if nobody has elbow room. It's less dense if we can all stretch and move and do yoga and dance and stuff. So that's close here. So if I just took that definition here, I would take frequency and divide by space. So for example, if I look back at my frequency chart, right there, this has 20, the space is 10 beats per minute wide, right, the 70s, 70 up to 79, 10 possible options for beats per minute. Those 20 people are spread out among those 10 possible values. Whereas in the 50s, there's only about 2 people in the 50s. So 2 people get to choose from all those possible 10 values. Lots of space in the 50s, densely packed in the 70s. Okay. If we looked at a box plot for this, we would find little thin, narrow boxes in the middle and wide boxes out toward the edge. Okay. Indicative of a bell shape. But actually, to do density with probability, we use relative frequency and divide by space. So if you notice, that's 50%. if I take 50% and divide by a space of 10, then I should get 5%. Does that make sense? Yeah. So that the first definition I wrote down is the physicist's point of view of density. We are going to modify that and say density for us is relative frequency divided by space. And what is space for us? Space for us is the width of a bin, the width of a group. Early on in chapter 1, we talked about different kinds of measurements that we might end up when we do surveying. And so let's see if we can do a little review of that. If I measure somebody's pulse rate, what kind of data is that? Can you guys tell me some words that describe this kind of data? Pulse rate. Think way back to chapter 1. Block this out. Oh, Kirsten.
On our test, it was like, what kind of blah blah blah.
Now, what kind of sample is it?
Just kidding, I don't know.
But I didn't ask this on the test, but it was in the homework. Anybody remember way back, chapter 1? Like ratio, nominal, ordinal. Remember all those different categories?
Oh, it's the one that is it the one that the numbers is so no, just kidding.
Yeah, it's related to numbers. Yeah, yeah. So our options were nominal, ordinal, interval, and ratio. Qualitative and quantitative. So I just went over the quantitative options. So is this data qualitative? Does it describe something in words, or is it quantitative, describe something in numbers? It's quantitative, okay. So if it's quantitative, is it nominal? Is it just a name using a number like my student number or my social security number? Or it's a ratio? So a ratio means that subtraction is important and 0 is important.
Well, if your pulse rate's 0, it's probably important.
You're dead, right? Yeah, I don't want my pulse rate to be 0 yet. I'm not ready for that. Yeah, so this is a ratio kind of number. Okay, so of ratio and interval kind of numbers, things are either discrete or continuous. Anybody remember what this one is? Discrete. Why is it discrete versus continuous?
Well, because continuous would mean that you are counting on, right? And
Discrete means you're counting.
Yeah.
Okay, so we're counting. Continuous means what? What can somebody give me an example of a data that we could collect would be continuous?
Like if somebody's
Height.
growing.
Height, growing, yeah. Because I could be 5 foot 8 and a half, or 5 foot 8 and a quarter, or 5 foot 8 and a little teeny bit more, right?
And
So-
it means more to your daughter than it does to you.
Yeah, 1 inch means more to my daughter than it does to me. Excellent. So this is an example of a discrete variable. Okay. If I randomly pick somebody out of the room, you're going to have your own pulse rate. What do you think your pulse rate is, Tanya? 70. Okay. I'm guessing mine is about 90 right now because I didn't sleep very well last night. That affects your pulse rate if you're tired. Coffee will affect your pulse rate. I stopped drinking coffee. I'm not drinking coffee. Even as excited as I get. It's just math that gets me this excited.
oh,
It's kind of weird. Elvia said that's never happened to her. It's math. Elvia, we're missing you today. So, what was my point? Oh, it varies like what your pulse rate is, right? And if I randomly pick somebody, then I have a random variable. I'm introducing a new terminology here, random variables. So we are going to be playing a lot with what we call random variables here. And in this case, our pulse rate is a random variable. There's nothing really random about an individual's pulse rate. But when I'm looking at a group of people and I randomly grab somebody, that's where the random comes in. Okay. I'll do some other examples of random variables in a minute. So in the future, we're going to be dealing a lot with random variables, and density is going to come up here and there. Density more often will come up with continuous random variables than with discrete ones. Okay. But I have right there a density histogram for a discrete random variable. So it's doable. It's just so like normal distributions are usually for continuous kind of ratio data. Could be interval. And they are always density distributions. Okay. So just make a note of that. Discrete distributions are usually relative frequency kinds. Continuous, normal distribution is usually continuous. At least it's always continuous. We usually use it to represent continuous stuff. Oops, normal, eraser. Is usually, oops. I want to say always, but there's probably an exception to the rule. Is usually a density distribution. Okay, who cares? Well, I'll show you why we care by looking back at my pictures. Okay, so discrete distributions are usually relative frequency, not density, but you can always make it into a density easy. Just divide by the width of each column. Continuous are almost always density distributions and almost never just relative frequency. Okay? And we have to turn them into relative frequency so we can answer questions about chance of something happening. So looking back here, again, if I want to turn a relative frequency histogram into a density, I just divide by the width of each group. Here I made the width easy, 10. It's easy to divide by 10. But the width could be 3 or 4 or 7 or 100 or 10,000. Just kind of depends. If I'm giving a density distribution and I want to convert back, right? So just like estimating the top of, or let's say the bottom, let's say this stack, number of people in the 60s. That's just under 0.25 for 0.025 for density, right? So let's say it's 0.024 maybe. That's not a probability. To change it to a probability, I undo the division by doing what? Multiply by the width. Yeah, so if we say, oh, the width is 10, 10 times 0.024 would be 0.24. So then the probability of somebody to have a pulse rate in the 60s is about 24%. So we can turn a density distribution into probabilities by doing a multiplication. Okay. So I'm just going to write that down in my little chart. Let's do another snip of this. And copy and paste. Position it better. So here, again, I'm going to focus on the 60s. The density for someone with a pulse rate in the 60s is approximately 0.024. To find the probability of someone being in the 60s, I just take the density and multiply by the width. So 0.024 times a width of 10 gives me about a 24% chance that a rate, oops, that's not a percent yet. Oh shit, wrong one. About a 0.24, 24% chance, approximately, that they have a pulse rate in the 60s. And later, when we use the normal distribution more and a couple of other ones, we'll have to make a couple of different choices. Is it a density thing I'm looking at, or is it a probability I'm looking at? Is it a cumulative answer I'm looking at, or is it a single answer I'm looking at? And we're always going to have to ask ourselves those questions to make sure we get interpretations of numbers right. And it's all about interpretations here. All right, so anything we've done a frequency distribution on, we can now change into a probability distribution or a probability density distribution. And chapter 4 is all about introducing us to these distributions, which we've really already been working with, because what is a distribution? A histogram, yes, it is a histogram. And we are good at making histograms now, right? We're getting better and better all the time. Okay, so some other examples. Coins, that's dice. coins. There we go. I mentioned the other day in class that I virtually flipped a quarter and a penny 2,000 times, 1,000 times each, and I ended up with this distribution of tails and heads. Well, what I did was I told the computer to give me a random number between 0 and 1, which means 0 or 1, a random whole number. And then I said a 0 is a tail and a head is a 1. And so then here I have penny was a tail, head, tail, 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 head, 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 tail, head, 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 and so on. So want to hear something cute? Those kind of thing. How didn't we have a hard time doing random before? Remember that? So you've probably seen this in these crime TV shows where they say, ooh, somebody doctored these books, and I can tell because there's way too many 5s on this page. Something like that. If I asked you to randomly write down, so I say, go home tonight and flip a coin 100 times. How many of you would say, oh, I don't have time to flip it 100 times. I'm just going to write down H and T 100 times in random order. Right? Kirsten, me, we're totally doing that, right? I could look at your beta and know you cheated and didn't actually flip the coin. How could I do that? Well, right here, I have a whole bunch of heads in a row. 1, 2, 3, 4, 5, 6. How many of you would start to feel not random enough if you wrote head 6 times in a row? Right? So we would be unlikely to write a whole bunch of heads or tails in a row. And out of 100 heads and tails, there's like a 90-something% chance that I'm going to find a group of 7 or 8 or 6. And you, though, trying to be random, are unlikely to do that, which is pretty weird.
I'm just like a really bad liar.
Me too. I'm a horrible liar too. But I'm trying really hard to be random, right? But you know, we're humans. How does it mean to be random? It's hard. Anyway, that's a cute little probability idea. Anyway, these are close to the same size, right? Yeah, so this one is like, just over 1,000. This one is just under 1,000. I expect out of 2,000 flips to get about 1,000 heads and 1,000 tails. And I got about 1,000 heads and 1,000 tails. So I think this coin is relatively fair. Okay. The mint that made the coin didn't design the coin to be fair. They designed the coin for exchange. But it seems fair enough. We played around the other day with, oh, I had a point, sorry. Another point here. Am I going to get a head or a tail when I flip? Yeah, right? I'm going to get a head or a tail when I flip, right? It could land on its edge, but it's pretty unlikely. So let's see. I'm going to type in something random coin flipping random.org. Oh, look at that, was cute. Oh. Google is so sweet. They do the nicest things. Head. Oh my gosh, this is new. This wasn't here last week. Because I typed the same thing in last week and that didn't come up. Nice. All right, so
Google knew and they're like, well, we got to do something.
they were watching. They know everything. Scary. My crazy stepfather. I love you, Bob. He got rid of his Google account because he's afraid they're watching too much stuff about him. Right. And I'm pretty paranoid too. I have a tinfoil hat at home I put on sometimes. But I like my Google account. Anyway, I don't know what the next flip is going to be, really. A head or a tail. It's up to chance. If they did their programming right, Google's pretty good at programming. I'm assuming they did. It's a tail.
Back and forth every time.
That time. What's that?
It just goes back and forth every time.
Was it?
It did heads 3 in a row. Oh, it did? Yeah, I did. That's funny.
Oh, there's another head. 2 heads in a row. Oh, 3 heads in a row. Oh, there's a tail. Okay, so yeah, so if I do this 100 times and I don't get 6 or 7 in a row, I'm going to write to Google and say, hey, something's wrong here. I should have. Probability says. I can show them the calculation, and their programmers will get it. They'll like, ooh, yeah, something's wrong. So anyway, and then let's suppose I keep doing this. I'm counting heads. Like I watched that Rosencrantz and Guildenstern video, and I'm stuck on heads. And so I flip it 10 times. About how many heads will I get? About 5 heads, right? And so, but I don't know. I could get 4, could get 6, could get 3, I could get 8, could get 9, could get 10. So it's random how many I'm going to get. but it varies also. So this is, again, a random variable. Okay. So random variables are actually all around us. We just weren't looking for them. Another example, contrived but cute. Dice. Well, let's see if Google has random dice. Oops. Random dice Buller. Oh, Google didn't give me one. I'm sure they're
Maybe
now.
just put like whole dice.
Oh yeah.
It was like really simple. Look at that.
Oh my gosh, Michaela, nice job. Okay. So we can roll it. I wonder if it'll let me roll 2. Probably not. Ooh, how'd I get there?
I'll take you to dice roll.
Okay.
But it says roll.
Okay, so we're rolling 2 dice. Okay, so I got a 6. Add them up, right? Roll them again. 9? I'm a little slow. Help me out here. 6. 8. 6. I got 3 6s so far. Huh. Am I more likely to get 6 than like 2 or 12? 11. Okay, what possible sums can I get? 2 through 12, right? Because I get a 1 and a 1, least, 6 and a 6 at most. Okay, so dice, 2 dice sums. The sample space is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay.
There's 5 possible outcomes for 6.
There's 5 possible outcomes for 6. What do you mean?
You can get a 1 and a 5, 4 and a 2, 3 and a 3, 2 and 4, 1 and 5.
Oh, right. Okay, so you went awfully fast there. So I could get like a 3 and a 3. I could get a 2 and a 4. I could get a 4 and a 2. I could get a 1 and a 5, or a 5 and a 1. So what Michaela did is she broke it down in a 6 is not rolling a sum of a 6 is not a simple probability because it's made up of multiple other options. Okay. And then I have 5 different outcomes possible for 6. So each of these pairs of rolls, that's an individual simple outcome. Simple means you really can't break it down any further. So the probability then looks like it's 5 out of what? 36. Why 36? 6 options for the first dice, 6 options for the second. 6 times 6 is 36. Okay, so I made a grid of this in Excel, and we were playing with, I think, a little bit last class, right? Coins and dice. Okay, so here's my grid right here. Let's blow that sucker up a little more. So I have die 1 across the top, you get a 1 through 6. Die 2 on the side, you get a 1 through 6. And those are all the sums. And so here I can see the 5 different 6s. So it kind of makes sense now that 6 popped up more than like 2 or 3 or a sum of 11, because there's more ways to get a 6 than there is a 2, a 3, or an 11. So these sums are not equally likely, even though each individual number on a dice is equally likely. I put them together in a new way, and that changes everything. That changes everything. I decided to make a histogram of it because I love making histograms. It's my favorite graph ever. So let's shrink this down a little so we can see my cute little histogram. So I have my different sums here, how often each sum occurs, right? I used the frequency function to have it count that grid there. I could have counted them by hand. I was too lazy. That's not the right word. I'm not lazy. Okay, so here's the histogram. Oh, where'd it go? There it is. Any comments about this histogram?
It's normally distributed.
It's normally distributed. It's bell-shaped. It's not quite bell-shaped. It's pyramid. It's like V-shaped, really. Yeah. Okay, so it's V-shaped, bell-shaped. Well, It turns out there's all different kinds of bells out there. And we could say, yeah, maybe this is kind of bell, but if we check the percentages, which we'll do in a minute, it's not bell-shaped. So I'll show you how to find the standard deviation of something like this. We will not do that often. No, we will not do that often. It's kind of a pain in the butt, but it's not too bad. We will find the mean. What sum am I most likely to get? 7? Okay. That's what I'm most likely. I expect to get a 7 more than anything else. Agreed? Okay, so that's the expected value of the sum. Okay. So playing around some more. Let's see. I did some other stuff here. Let's delete this and redo it. And delete that. All right. Frequency. What's the other thing we're going to like to do now a lot more besides frequency is not density, relative frequency. We'll do more often than anything else. So I'm going to calculate some relative frequencies here. Let's blow this up so it's more visible. Oh, so let's call this rel frequency. And to do that, I just take whatever number the frequency is and divide by how many things could have happened, which is what again? 36. And once I type that, I can just fill it down. Oh, slow down there, Tiger. And let's make that a little wider and reduce the number of decimals to maybe 3. There we go. Okay. So like there's a 2.8, almost 3% chance of getting a sum of 2. There's a, let's see, 7 has about almost a 17% chance of getting a 7. Okay. So next, I want to remind you of a formula that we looked at but didn't use very much. We only used it a tiny little bit in class. And that formula relates to how to find the mean from a frequency table. So mean of a frequency table. So I have a table of, I'm going to call them X values here. I have a table of relative frequencies. Okay. Oh, I got a question for you. Let's look back at this particular cute grid here. The relative frequency of getting a 7 is about 16.7%, right? Question, what is the probability of getting a sum of 7 when I roll 2 dice? 6 out of 36, which would be what is the percentage?
16.7.
Maybe 16.7%? So what's another word for relative frequency that starts with a P?
Probability.
Probability, yeah, relative frequency and probability are the same damn thing.
I feel like said that like 3 days ago because I was thinking that it was like similar, but not like I had to do the work to find probability when I did this.
Yes, relative frequency is probability. Okay, so Michaela will never forget that now because she had to work hard and now she knows. So back here, so instead of calling that relative frequency right there, I could just call it probability, couldn't I? I'm going to call it P for probability. So for example, for us, we have X is 2 and the probability is like 0.03-ish, and X is 3 and the probability is roughly, I'm not going to write them all down because they're here, about 6%, right, and so on down the line. The rule for finding a mean from a frequency table like this was to add up all of the things we were looking at times their frequency or relative frequency. So that's the new rule. The old rule looked like this. Take the sum of the x's times their frequency. So how many times did each x happen? Divide by the sum of the frequencies. Okay, let's think about that. The sum of the frequencies. The sum of the frequencies, what does that mean? Back here, frequencies. It occurred once, it occurred twice, it occurred 3 times, and so on. What's going to happen if I add up all those frequencies in this case? What are those frequencies going to add up to?
36.
36. Is this 36 things that can happen? Yeah, so let's double check. They should add up to, let's go away box. they should add up to 36. Please stand still. Come on. Oh, darn it. Click, click, there we go. Close, no big surprise, there's 36. Okay. And 36 is what we used to call n. Right? N is the total number of things we have and have to look at. So just review of some other formulas. That's the same thing as taking the sum of all the x values times their frequency divided by n. With me?
Is that thing in the front, that's sum?
Sum, yeah, that's that Greek sigma, means sum. So capital Greek. Oh my God, that's supposed to say Greek right there. Sigma. And it means sum. It appeared in the book a few times. So add stuff up. So I'm just going to tweak this formula a little bit, do a little algebra on it. Actually, I should probably do a simpler example. No, that's okay. I can use this one. My claim is that I can rewrite this as the sum of the x's times the f's over the n's. And I'll just illustrate that with the example of the dice. I could have gotten a sum of, oh, what happened? I could have gotten a sum of 2. That occurred once. I could have gotten a sum of 3. That occurred twice. I could get a sum of 4. That occurred 3 times. Right? And I'm not going to do all of them because I'm lazy. And then, let's see, I could have gotten a sum of 11. Anybody remember how many times 11's happened? 2 times, yes, 2 times. And then a 12 can happen once. Okay. So if I add up all of those guys and divide by 36, that should give me the average value of what we're going to get when we roll. And I'm just going to do a little unaddition here. You might ask, what is unaddition? Well, here's what unaddition is. So I'm just trying to justify my formula, then we'll actually use it. Oops, 36. If I look at this in reverse, if I have a whole bunch of fractions and they all have the same denominator, isn't the rule to keep the denominator and then just add up the numerators? Yeah, so this is what I mean by unaddition. I'm unadding those for a minute. Why the hell would you do that, Gary? Well, because 1 over 36, 2 over 36, 3 over 36, what do these numbers represent compared to their sums? Fractions of what? What's the fraction mean here?
The possible outcomes.
That's the probability, isn't it? Isn't there a 1/36 chance of getting a 2 and a 2/36 chance of getting a 3? Okay. So this formula right here was given in the book earlier, back in chapter 2. My claim is it's the same formula as the x's times their probabilities. A relative frequency is the frequency over the amount of things that can happen, which is also a probability. Okay, so here is the point of that whole bit of madness. Scrolling down. If we have a probability distribution table, then that means we have a bunch of x values, like how many boys are in your family, or how many times did you get heads, or what was the sum of your 2 dice, times their probabilities. So we have a whole bunch of stuff down here. We're often going to want to find the average value of the situation. Average. What's another word for average? Mean. Yup. And I'm going to give you another word for it in just a minute that's very powerful. And to find that mean, all you have to do is multiply the x's times their probabilities and then add them up. That is the mean. And this is a symbol that's used more often in probability for a mean. mu. Remember the Greek mu that came up for? What did we use mu for earlier in the course? It was the mean of what kind of situation? We had mu and we had x bar. They each had their different roles. They're both means, but one's for one thing, one's for another thing. Anybody recall what?
For the path. Sample or no?
Yeah, x bar was for the sample, and mu was for the population. Okay. If I have a probability distribution table, then what that means is I'm doing theoretical probabilities most likely, and theoretical probability means I have complete knowledge of the situation. If I have complete knowledge of the situation, I must have the population. Okay, so that's why mu is used more often for the mean in this situation, when we're talking about probabilities.
So the mu is the one that goes with the population.
Yes,
The sample.
x bar goes with the sample, yeah. And depending on the situation, we'll go back and forth between them, but you're gonna see mu popping up in the book here and there from now on. And that just means the mean, the average value of the distribution. So let's find it here. So I have this table in front of me. So all I have to do is multiply the sums times the relative frequencies, the probabilities. So off to the side here, I'm going to call that x times p. And I'm going to say, computer, please multiply the sum times the probability. Fill it down. It's a lot of work, huh? Not really. And then what do I want to do with those sums, those products? Oops, I gave it away. Add them up. I want to sum them. Yeah. So I want to know what is the sum, because that's going to equal what we call the mean here. Oops. Oh, I know. You didn't like that. There we go. Now you like it. So equals sum, add the numbers above. And I get an average value of 7. Interesting. 7 was also the tallest stack. It's what we expect to have happen more often than the others. So another name for mean, when we're talking about probabilities, it's called expected value. What do you expect to have happen? We expect to see a 7 more often than anything else. And so this terminology is going to come up too from now on. So the average, the mean, is also referred to as the expected value. One more example, then I'll shut up. Expected value. There's a shortcut to all that work, so I'll just demo the shortcut real quick here. I have to both do products and take a sum. So I might ask the computer, I wonder if you could do a sum and a product at the same time. Oh, look at that. There's a formula called sum product. And what that does is you give it 2 columns, and it multiplies row by row everything together, then adds them up. So if I have the relative frequencies, I can find the mean by using the sum product command and saying I need this column combined, oops, wrong button. Oh yeah, that's right. Combined with this column. So then I don't have to do that extra, oops, no, wrong one. I want that column. I don't have to do this extra row of multiplications. And I'll demonstrate this on a different problem. All I need is the sum and the probabilities. And it says 7, okay? So let's make a note of that, and then we'll do the next example. So this right here on Excel and any other spreadsheet, Excel, that says Excel. Again, you have to have a probability distribution table. So you need a column of numbers and a column of relative frequencies. All you do is use the formula sum product of wherever your x's are and wherever your p's are. Maybe I should call those x's and p's. Okay, so here's the next example. We'll apply that to it. And this one's a relatively simple one. Families with 3 children. We did a more complicated one in class the other day. What were we doing, like 5 children or something like that? And so what I want to do is I want to count the number of girls. Okay. So my brother has 3 kids. He's got 2 girls and a boy. He has 2 girls, right? But he has a friend who has 3 kids, and now my brother had girl, girl, boy. His friend had girl, boy, girl. So there's different ways those 2 girls could pop up when those births happen. But so counting the number of girls, that's my random variable x here. Let's see, what's the least number of girls a family of 3 kids could have? 0, right? It could be 3 boys. Good luck. I could also have 1 girl. I could have 2 girls. And at most, I can have 3 girls because there's only 3 kids. So what I want to do now is I want to find the probability of each of those things happening. Okay, so let's think about this for a minute. Just on the first child, what's the probability of having 1 girl? It's 1 out of 2, okay. What's the probability of having a girl for the first child and a girl for the second child? Okay. Another way I could write that is what's the probability of having a girl first and a girl second? What do we usually do with ands? You multiply them, and you can multiply straight without having to do any other fiddling if they're independent events. So is it true that having a girl already, I'm still equally likely to have a boy or a girl later? Is that true? Remember that crazy video we watched the other day? Yeah. Birth stuff's kind of funky. There's a lot of weird stuff going on there. There's some evidence that the gender of your first child has some effect on the gender of your next child. Let's make believe it doesn't, that they are independent. So that means I can just say that's 1/2 times 1/2. Or a quarter. What's the probability that I get a girl first, a girl second, and a girl third? One out of 8, because it'd be 1/2 times 1/2 times 1/2, right? Beautiful. And that should be 1/8. Okay. Now, scrolling down, just playing around a little more. What's the probability I have a girl first, a girl second, and a boy third? Half times 1/2 times 1/2. It's still 1/8. Okay. All right. Now here's the problem, though. So I'm hesitant to say that the probability of having 2 girls is 1/8, though, because there's different ways that can happen. It could have been girl, girl, boy. It could have been girl, boy, girl. It could have been boy, girl, girl. Those are the only ways, right? Yeah. The single boy has 3 places it could have been born: first, second, or third. So what do you think the probability of having 2 girls in any order out of 3? If there's 3 ways that 1/8 could happen. 3 out of 8. Yeah, there's 3 ways that 1/8 thing can happen. So it should be 3 out of 8. Yeah. So in other words, what I'm asking here is what's the probability of having a girl first, or, oh, sorry, no, the boy would be first, or the boy could be second, or the boy could be third. That's boy. Well, independent, is it totally a different situation having a girl, boy, girl than a girl, girl, boy? It has 2 different scenarios, yeah. So they are mutually exclusive. So that means I should be able to take the 1/8 of this plus the 1/8 of that plus the 1/8 of that. So there's a bunch of different ways to think about it. So far we have 2 different ways. They both lead, oh, my pen is freaking out. There we go. They both lead to 3/8. What other tool could I draw upon to figure this out?
A tree.
A tree, yes. I could draw a tree to figure this out, right? I'm going to leave you guys to do that later if you wish. So here's my belief then. The probability of no girls is 1 out of 8. The probability of 1 girl, well, that's like having 1 boy, just mirror images, that's 3 out of 8. Probability of having 2 girls, 1 boy, we just figured that's 3 out of 8. And the probability of having exactly 3 girls is, what do you think? 1 out of 8? Okay, to test this, what do those probabilities add up to? 8 out of 8, which is 100%. And if we have all knowledge should add up to 100%. Oh, so we're on a good track here. We think we got that right. A tree would verify this. All right, so I'm going to plug this into Excel. How many girls am I most likely, how many girls do I expect to have? If I grab all families of 3 that exist, and I added up how many girls they had, divided by how many families, how many girls would I expect to find on average? What is it? 1/2, almost.
Would you think like,
Yeah.
I would say like 30%.
About 33%.
One.
Well, no, how many girls though? How many girls in a family of 3?
All girls.
1 to 2.
Between 1 and 2, right? Isn't that, like, those have the same probability, right? Yeah, so I would expect most families have 1 or 2 girls in them, of 3 kids. There's fewer that have none, and there's fewer that have 3, because those are less likely to happen, right? So on average, so let's calculate the average. So I'm going to whip this into my spreadsheet. Okay, so we have X's, which are girls here. I could have 0, 1, 2, or 3. My probabilities here, make that column a little wider so it's easier to read, are equal to 1/8 or equal to 3/8. Oops, wrong spot. Enter, there we go. Equals 3/8 equals 3/8 equals 1/8. Now again, this is pretty easy to do by hand, but we're going to have bigger data sets. We're going to want to use the computer as often as possible. So to find the mean here, what I'm going to want to do is tell the computer to multiply these guys together, then add them up. And that's what sum product does. So I go equals SUMP. On Excel, you'd hit tab. On Google Sheets, you hit enter. And then I say, okay, I want these guys, comma, these guys. You got to comma separate them. You can't just grab them all at once because it needs to know how to separate them out. Close parentheses, hit enter. 1.5 girls. That's like 1 or 2, right? Now, the mean is definitely 1.5, right? Hey, Mom, on average, families of 3 have 1.5 girls.
You can't do
My mom's like, whatever. My stepfather would be like, why, you gonna count one of the girls now, Gary? Right, he'd be all over that. What is that? That's bullshit, you would say. Another dollar on the bill. So, yes, Bob, it is. So what that means is, on average, they would have 1 or 2 girls. I know we can't have half a girl. That would be bad. Hey, well, it is what it is. Okay. I'm going down a weird road. I'm going to shut up. But I can't say the average is 1.5, even though it technically is. It's 1 or 2 because these numbers are discrete. It's not continuous data. It's discrete data, so I got to say it's 1 or the other. Okay. What if it came out to 1.2?
Would be a really ugly girl.
So it's still 1 or 2, more likely 1. Right? Here it's 1 or 2, even chance. Right? So how could it be possibly 1.2? Well, I think I might have told you this story the other day. I grew up in Rhode Island. And in Rhode Island, there's a lot of industry. And along with industry, there was a lot of pollution back when I grew up in the 70s. And so I drank water that, probably shouldn't have been drunk by people because it was polluted. A lot of dioxins. And there's some evidence that heavy intake of dioxins in your youth makes you more likely to have girl children later. Okay, and I had 2 girls. My brother has 2 out of 3 that are girls. Yeah, interesting. 2 data points, not really enough information, but sketchy. So maybe, now I'm exaggerating greatly, but let's say because of those dioxins in the water in Rhode Island where I grew up, that the probability of having a girl jumps to like 60%. It's not that high. It's more like maybe 53, I think it goes up to. But I need this to illustrate my point. And then this jumps up to, jumps down for boys to like 40%, right? So that's going to skew things. I'm more likely to have girls, and so the probability back in my table right here, it's going to jump. That 37.5 is going to be higher. Okay. So in the next class, we're out of time, I'll show you how to tweak this for unequal probabilities. Okay. And this kind of scenario is what section 3 in the book is all about, chapter 4, which we'll get to next week. I just want to give you a heads up before this weekend. It's called binomial probabilities. Bi. What's bi usually mean? 2. There's 2 things that can happen. A boy or a girl. A head or a tail. Basketball player. It's either in or it's out.
Your basket's probably out.
Okay, mine's probably out, right? Yeah, so there's all kinds of binomial problems all around us. So the 2 most common kind of probabilities we'll see in the future are related to binomial and normal. and we're going to spend the rest of the term studying those two things. Okay. Fun. Yes. Okay. Go forth. Do good math and other stuff. I'll see you all. I'll see some of you Friday and the rest of you Tuesday.
Have you ever seen Cloudy with a Chance of Meatballs?
Yes, I have seen Cloudy with a Chance of Meatballs.
Remind me of